Hello everyone, my name is Amit Chaudhary. Here is the topic of organic chemistry, that is alkane. In this topic, the content is definition of alkane, structure where sp3 hybridization we will see, some general methods of preparation of alkane where we will see Wurtz reaction in detail, then general reactions of alkane where the halogenation reaction we will study in detail, and lastly the uses of alkane. According to IUPAC, the definition of alkane is acyclic branched or unbranched hydrocarbons having the general formula, that is CnH2n plus 2, and therefore it contains hydrogen atom and saturated carbon atoms. Okay, now when you are going to define alkane, acyclic hydrocarbons, this formula and the saturated, these words are important. Okay, the simplest, because the alkane are simplest saturated organic compounds which are made up of carbon and hydrogen only. The other name or the synonym of alkane is, it is also called as open chain saturated hydrocarbon or acyclic saturated hydrocarbon, and the well known synonym of alkane, that is paraffin, which means a compound which have low chemical reactivity, and this is the general formula of alkane. The structure of alkane depends on the hybridization of carbon, that is sp3 hybridization. And when we want to study the sp3 hybridization, the first thing we have to look, that is valence shell electron configuration of carbon. At ground state level, carbon have 4 electrons on outer shell. This 2s orbital contains 2 electrons, 2px and 2py orbitals have 1 electron, and here is the empty orbital, that is 2pz. Now before going to sp3 hybridization, carbon reach to excited state where this second electron of 2s orbital jump to higher level orbital, which is 2pz. So here is the excited state configuration of carbon, and after reaching to this state, the all 4 orbital mixed themselves and gives hybridization orbital, that is sp3 hybridized orbitals. If you see, the 2s orbital is mentioned below and this p orbital are mentioned above, because these are the orbital of higher level and 2s orbital is the lower level. And if you see, this sp3 hybridized orbital are mentioned between pz orbital and 2s orbital, because these orbital have mixed energy of p and s orbital. So they have energy in between the energy level of p orbital and energy level of s orbital. So this kind of representation of orbital are important when you are explaining the sp3 hybridization of carbon. Here is the shape of sp3 hybridized orbital, which is made up of 3p orbital and 1 round shape s orbital. If you see the shape of hybridized orbital, which is similar to shape of p orbital, but the difference is sp3 hybridized orbital have one lobe which is higher in size than the other lobe. To make sp3 hybridized orbital, we need 4 orbitals, in which third portion is of p orbital and one portion is of s orbital. So we can say that this sp3 hybridized orbital have 75% p character and 25% s character. Here is the orientation of sp3 hybrid orbitals on carbon. This orientation is tetrahedral. We know orbital is a representation of electron and there is repulsion between electron, likewise repulsion between orbitals. So these 4 sp3 hybridized orbitals arrange themselves in 3 dimensions with optimum distance, which makes 109.5 degree angle, and it gives tetrahedral nature. Here is the orbital representation of methane, where sp3 hybridized orbital of carbon interact with s orbital of hydrogen and makes covalent bond. You can represent as a molecule where there is 109.5 degree bond angle between CH bonds of methane. First method of preparation, that is catalytic hydrogenation of alkene or alkyne. If we use alkyne as an reactant, it is reacted with hydrogen gas using heat and nickel as an catalyst. It is converted to alkene first. Then this alkene convert into alkane using same reaction condition. In place of nickel, we can also use platinum or palladium as an catalyst. Normally, this reaction is used in conversion of unsaturated fatty acid into saturated fatty acids. Here is the example where one hexene is converted into hexane using catalytic hydrogenation. Now, preparation of alkane from alkyl halide. The first reaction, where alkyl halide is reacted with zinc metal in presence of acid, which gives alkane. The second reaction, magnesium is used and the solvent, which is dry ether. So we can use diethyl ether as a solvent. So this reaction is Grignard reaction, which gives organomagnesium halide, or you can say as organomagnesium reagent. And this reagent, when we add water, it gives alkane. This method is called as Zerwitznov method. In third reaction, alkyl halide is reacted with lithium metal, where the solvent is dry ether, which also gives organometallic reagent, and this reagent is further reacted with copper halide, which gives Gilman reagent, which is diorganocopper. This reagent again reacted with a second alkyl halide, which gives alkane as a product. Next reaction, where we can convert alkyl halide into alkane, that is Wurtz reaction. Here alkyl halide is reacted with sodium metal and the solvent is dry ether. It gives alkane. If you see here, the product which is formed have double number of carbon than the original reactant alkyl halide. So we can say that if you take a butyl halide or butyl chloride as an reactant, you will get octane, double number of carbons. Mechanism of this reaction comprises with two steps, where the step number 1 is single electron transfer mechanism. Over here there is mechanism is explained by moving of single electron, and the arrow pushing mechanism contains fish hook arrow. So what is happening here? There is homolytic cleavage of alkyl halide bond, where one bonding electron is taken by this halogen and it reacts with sodium, which gives sodium halide. Now this alkyl group takes its bonding electron and it will convert into radical. This radical will react with sodium metal and it gives carbanion. The second step is substitution nucleophilic bimolecular reaction, where this carbanion attack to this alkyl halide, which is our reactant. There is removal of this halogen and bonding between both alkyl groups, which gives alkane. Here is the explanation of both steps of mechanism. Now the limitation of Wurtz reaction is we can use this reaction to synthesize symmetric alkane or symmetrical alkane. Now what do you mean by symmetrical alkane? It means the center of molecule divides the whole molecule into two equal parts or two symmetrical parts. Here is the example where 2-chloropropane is converted into 2,3-dimethyl butane. Next method, from the carboxylic acid we can get alkane. Here is the first reaction, that is Duma's decarboxylation, where carboxylic acid salt is treated with soda lime, that is sodium hydroxide plus calcium oxide. Upon heating, this salt is converted into alkane. The second method, that is Kolbe Electrolysis. It is electrochemical oxidative decarboxylation of carboxylic acid. Here is the reaction where upon electrolysis of carboxylate salt, it is converted into alkane with the liberation of carbon dioxide and hydrogen gas. If you say electrolysis, there is cathode and anode. On side of cathode, carboxylate salt liberates 2 electrons and convert into carboxylate radical, and further degradation of this intermediate, there is liberation of carbon dioxide and formation of alkyl radical. Now 2 alkyl radical gives alkane. Now on cathode side, 2 molecule of water gains 2 electron, that is reduction process, and converted into hydroxide anion and 2 hydrogen radical, which gives hydrogen gas. Next is the conversion of alkane from aldehyde and ketone. We have two reactions. One is Clemmensen reduction and second is Wolff-Kishner reduction. So here is the reduction of carbonyl compound to alkane. In Clemmensen reduction, the reagent which is used is zinc dissolved in mercury, which is amalgamated zinc. The condition is acidic condition. In Wolff-Kishner reduction, hydrazine is used as a reagent and the reaction is performed in basic condition. So here the main difference in the reaction condition is Clemmensen reduction performed in acidic condition and Wolff-Kishner reduction is performed in basic condition. So if you have any carbonyl compound which is base sensitive, so at that time you are going to perform Clemmensen reduction. Okay, and you can also use Wolff-Kishner reduction for any carbonyl compound which is acid sensitive. Now we will see reactions of alkane. The first reaction is halogenation reaction, where alkane is reacted with halogen gas which gives alkyl halide. This reaction we can perform as a thermal reaction, or we can also perform as a photochemical reaction. Next is the nitration using nitric acid and sulfonation using sulfuric acid. Alkane bonds and gives carbon dioxide, water, and much more important, that is heat. This is oxidation reaction of alkane. In every home, in gas bottle, propane and butanes are there, which on burning gives heat which is used for cooking purpose. Next reaction, that is pyrolysis or cracking, where the macromolecule of alkane is converted into smaller alkanes. It also gives alkenes. Pyrolysis or cracking, it is the chemical process by which heavy hydrocarbon molecules are broken up into lighter molecules by means of heat and usually pressure, and sometimes there may be use of catalysis also. The simple definition is the compound decomposition by the action of heat alone is known as pyrolysis, which means cleavage by heat. Majority cracking process is used in petroleum refining, where cracking converts straight chain hydrocarbons that are poor fuels. They are converted into branched chain compound which have high efficiency as an fuel. Types of cracking: there is thermal cracking, where the use of temperature and pressure is there for cracking purpose. Catalyzed, if catalyzed are used, it is called as catalytic cracking. We have hydrocracking also, where hydrogenation is also performed in cracking process. Steam cracking, where there is use of water as steam at 700 to 900 degrees Celsius. The mechanism of pyrolysis, it follows free radical reaction. Here is the example where there is pyrolysis of propane. Upon pyrolysis, there is homolytic cleavage of carbon-carbon bond, which gives methyl radical and ethyl radical. Now, methyl radical further react with propane and it gives a propyl radical. Now, there is homolytic cleavage between carbon-hydrogen bond, which gives propene and hydrogen radical. Now here this ethyl radical convert into ethene and hydrogen radical, and both the hydrogen radical gives hydrogen gas. Halogenation of alkane, which is also called as free radical chain reaction of alkane. Alkane is reacted with halogen which gives alkyl halide. We can use heat or sunlight. The important thing over here is in halogenation the preference for the carbon is tertiary to secondary to primary. The reactivity of the halogen, where chlorine is most reactive than bromine, and in product isomerism is also possible, We will see these things in detail. Here is the mechanism for any free radical reaction. We have three steps, where the first step is chain initiation, which is there is homolytic cleavage of sigma bond of one reactant. Here we have halogen. There is homolytic cleavage. Free radical reaction mechanism is always explained by fishhook arrows, which indicate transfer of single electron. So over here, homolytic cleavage of sigma bond gives two radicals of halide, that is halide radicals. Next step is chain propagation reaction, which is conversion of one radical to another radical. Here we have three kind of molecule in our reaction: halide radical, alkane, and halogen gas. Here there is a reaction between halide radical and alkyl halide, where there is also homolytic cleavage between carbon hydrogen bond, which gives hydrogen halide and alkyl radical. So this homolytic cleavage, one electron is taken up by hydrogen and one electron taken up by alkyl group, which gives alkyl radical. In second step, alkyl group react with halogen, which gives alkyl halide as an product. Third step, that is chain termination reaction, which is conversion of free radical to normal molecule. If you see in our previous slide, chain initiation reaction gives normal molecule to radicals. Propagation means conversion of one to another radical, that is we have halide radical as a reactant, and when we get a product we have alkyl radical. Over here alkyl radical to halide radical, so it's a propagation. And in termination, two radicals react and gives a normal molecule. So conversion of free radical to normal molecule. In first reaction, halide radical and alkyl radical gives alkyl halide. Two alkyl radicals reacts and gives alkane, and over here two halide radical gives halogen gas. These are the side product. This is our main product, that is alkyl halide. Here is the reaction coordinate diagram of halogenation of alkane. Alkane gives first alkyl radical and then we get alkyl halide. In reaction coordinate diagram, it indicates potential energy versus reaction progress, where we can see the relative energy of our reactant, product and intermediate with transition state, which can also mention with activation energy. In this reaction, alkane is first converted into alkyl radical. So we have the reaction coordinate diagram over here. So it represents this conversion. In the transition state, we can also see the molecular connectivity. If you see in alkane, the CH bond breaks and we get alkyl radical. Now this H is taken up by halide radical. So this kind of interaction we will see in transition state. So it is better zoom in this reaction, where if you see there is partial bond breaking process is there, and here is the partial bond making, and we will see a relative radical charge on carbon and halogen. So this is the molecular interaction in transition state. Here is the example of halogenation, which is chlorination of propane. We have propane reactant and chloride radical. Here chloride radical may abstract hydrogen from carbon number 1 also, and there is also probability that chloride radical can abstract hydrogen from carbon number 2. If you see, carbon number 1 have primary hydrogen, carbon number 2 have secondary hydrogen. So we can get two kind of radical. That is, if this chloride radical abstract primary hydrogen from here, we will get primary alkyl radical as an intermediate, while if chloride radical abstract from hydrogen from this second position, that is abstraction of secondary hydrogen, we will see this kind of alkyl radical. And because here is the primary radical, and here is the secondary radical, we also get two type of isomer of alkyl halide. So in halogenation reaction, isomerization is also possible, and the rate of abstraction of hydrogen atom is tertiary, prefer first, then secondary, and then primary. Here is the second example where we see ease of abstraction of hydrogen atom with an energy of activation. Butane molecule is reacted with bromine in presence of sunlight. Here also bromine may abstract from carbon number 1, that is primary hydrogen, or it may abstract hydrogen from carbon number 2, which have secondary hydrogen. So in this reaction also we will get two kind of structural isomer, that is 1 bromobutane and 2 bromobutane. Now if we see 2 bromobutane, we get 98%, then here 1 bromobutane we are getting only 2%. So predominant product, that is 2 bromobutane. So we can say that the relative is with which the different classes of hydrogen atom are abstracted, that is tertiary, then secondary, then primary, and that is methyl hydrogen. This is because of our product or the intermediate radical are generated, their stability influences the ease of abstraction of hydrogen. So we know that the more stable is the free radical, the more easily it is formed, and the relative stability of radical is over here, the tertiary radical is most stable, then secondary to primary to lastly methyl radical is least stable. Ease of abstraction of hydrogen atom is also explained by activation energy. Here is the reaction coordinate diagram of alkane and bromide radical reaction, where there is chances of formation of tertiary, secondary, or primary alkyl radical. Because the general structure of alkane, there is presence of primary, secondary, or tertiary hydrogen also, by abstraction of which we may get a particular tertiary, secondary, or primary radical. Now if we see, to generate tertiary radical we have transition state over here, and to get primary alkyl radical we have transition state over here. So we can say that to reach transition state to get tertiary radical, we need less activation energy. So we need lesser energy to generate tertiary alkyl radical. So if there is possibility to get three type of radicals, the more radical which is formed, that is tertiary radical, because activation energy is less to generate intermediate of tertiary alkyl radical than secondary to primary. Okay, we can see in this reaction coordinate diagram. The next part is reactivity and selectivity, or chlorination versus bromination in alkane. Reactivity selectivity principle statement is that the more reactive a species is, the less selective it will be. So any species, if it is more reactive, then it is less selective. We have an example for that, that is bromination of propane. We have two type of hydrogen, primary and secondary. So obviously we can get two type of structural isomer as an product, that is one bromopropane and two bromopropane. Now if we see the relative percentage of isomer formation, one bromopropane form only 1%, while two bromopropane formed predominantly, that is 99%. We have second type of halogenation, that is chlorination, with same reactant, that is propane. The structural isomers formed, the percentage is 1 chloropropane 45% and 2 chloropropane formed with 55%. So we can see the difference of isomer formation. Over here 2 bromopropane formed predominantly 99:1 ratio, while in chlorination 2 chloropropane formed 55% and 1 chloropropane is 45%. So the ratio is not more different in chlorination than in bromination. So over here we can say that bromination, there is some kind of selectivity to form 2 bromopropane predominantly than chlorination reaction. The different percentage distribution in product is more seen in bromination than chlorination. So we can say that the percentage product formed in this reaction indicate bromine is more selective than chlorine. If we say the reactivity, it depends on energy of activation, or we can say that activation energy. Activation energy is best represented by reaction coordinate diagram. Here we have two type of reaction, chlorination and bromination. We will see propagation step of both, where alkane is converted into alkyl radical. Here is the chlorination and bromination reaction coordinate diagram. So in this particular step, if we compare the reaction coordinate diagram of both chlorination and bromination, over here the energy of reactant is higher than energy of product. So chlorination is exothermic process, while we will see in bromination the energy of reactant is lower than energy of product. So bromination is endothermic process. Now if we see the activation energy in chlorination, it is 60.8, while in bromination the activation energy is 75.6. So we can say that the activation energy of chlorination is lower than the activation energy of bromination. As the activation energy for the chlorination is lower, it gains early transition state which have energy which is similar to the energy of reactant. So chlorination is much more reactive than bromination reaction. So we can conclude that chlorine is more reactive than bromine. The second thing is because it needs less time to reach transition state or to convert into product. Chlorine cannot differentiate to abstract primary hydrogen, secondary hydrogen or tertiary hydrogen. So all type of possible primary, secondary and tertiary alkyl radical is possible in chlorination reaction. So we can say as chlorination is less selective to form structural isomers as an product, while the same thing if we see in bromination reaction have much more higher activation energy, that is 75.6. So more energy needed to reach at the transition state, and here the transition state is late transition state. The energy of this transition state is similar with the energy of product, because more time needed to reach a transition state, or we can say that more time needed to convert our reactant into product. It have sufficient time, bromide radical have sufficient time to discriminate primary hydrogen, secondary hydrogen and tertiary hydrogen. So bromide radical at that time predominantly abstract tertiary hydrogen and gives tertiary alkyl radical as predominant intermediate, and we will get tertiary alkyl halide predominantly as an product. So at that time bromination reaction is more selective than compared to chlorine. Here is the explanation of previous slide, that is chlorination is exothermic. Chlorination have 16.8 activation energy and the transition state is closely resembled to the reactant. So chlorination is more reactive and it have less time to attain transition state. So all possible type of isomeric product form nearly same percentage, and that's why chlorination reaction is less selective. In bromination, activation energy is 75.6 kJ per mole. Transition state is closely resemble with the product. It is less reactive, and because of less reactivity, bromination have sufficient time to reach transition state. So it have sufficient time is available to discriminate, to differentiate different type of hydrogen, and therefore it produce a specific type of isomeric product, that is tertiary predominantly than other structural isomers, other type of product. So bromination is more selective. Next one is the use of alkane. They are used as raw material in organic synthesis, gasoline, lubricating oils, fuels in engines and rockets. Natural gases like propane and butane are used in for heating and cooking purposes. Paraffin wax which is a white or colorless soft solid, is used as a lubricant, candles, crayons, electric insulations. Liquid paraffin, which is very highly refined mineral oil, is used in cosmetics and medicines. White soft paraffin, which is also called as white petroleum jelly, Vaseline, white petrolatum, is used as moisturizer to treat or prevent dry and rough skin. Here is the end of the topic. You can refer these three books: Ball and Ball, Mehta and Mehta, and Morrison and Boyd. Thank you.